Okay, we will start our discussion on mini hydropower plant design and integration with DC microgrid. And the present topic is identification of hydropower development opportunities and locating the diversion weir for a given project as an extension of a previous discussion. The objective of hydropower scheme is to convert the potential energy of mass of water flowing in a stream with a certain fall to the turbine, termed the head, fall is termed the head, into electrical energy at the lower end of the scheme where the powerhouse is located. The power output from the scheme is proportional to the flow and the head. So, the equation for the power generation, which we will be looking at a later stage, efficiency into Q rho G H, where Q is the water flow rate, cubic meters per second, H is the head of the project, G and rho are constants, rho being the density of water, G being the gravitational constant. So development of a hydropower project means finding a Q and finding H. So we earlier looked at classification of small hydropower projects based on the capacity, pico, micro, small hydro and large hydro and so on. But there is another classification based on the head called high head project, medium head projects and low head projects. High head projects are generally 100 meter and above as the head H, and medium head ranges from 30 to 100 meters. Low head 2 to 30 meters. You can see even 2 meter head can be a viable project. You can see that as per the power equation, Q rho G H. When H is small, H goes down, Q need to be high. Therefore, these small head projects are really handling in large rivers where volume of water is high, but the drop is small. When the drop is small, H is small, but since the Q is large, maybe 30, 40, 50 cubic meters per second, then power is good enough. And present day, there is another category called ultra low head projects. Ultra low head projects are less than 1 meter head. So, they come in large rivers across which dams are built for multi-purpose, and you can create about 1 meter head, and that on that we will see some configurations in the coming up slides, that you can embed turbines and generators within the dam itself, so that there will be a series of turbines and generators along the dam generating power. So, I have seen similar power plants in large rivers in Germany and so on, Rhine river and so on. So, they have built dams and embedded large series of turbine generators which are generating electricity. Because Q is high, they can be of sufficient capacity. So, cite this classification based on head. You will hear these terms in the industry. High is that high head project, medium head project, low head project. Cost wise and development easiness wise, high head projects are the number one. So, in a country when mini hydropowers are developed, first they begin with high head projects because they are straightforward configurations and economically more viable. Then you go to medium head, and once you finish the medium opportunities also, you go to low head projects. So, in low head projects, the civil components are fairly big, civil structures are fairly big, therefore, a little bit more expensive because large volumes of water have to be dealt with. You have to have wells and other things where they need to handle big quantities, Q. Maybe Q may run into say 50 cubic meters per second. You can think of how to handle that, 50 cubic meters per second. So, to civil structures will be fairly big, inlet valves will be fairly big, and the piping and other things will be fairly big, although they are short. Since the head is small, penstock equivalent part will be short, that is true, but the diameter will be huge because you have to handle 50 kind of cubic meters per second kind of flow rates. So schemes are runoff river schemes that we looked at in the previous session, and schemes with powerhouse located at the base of a dam. So in this here we are looking at some configurations possible for implementation of hydropower in various other forms of opportunities, not in hilly areas where you have high yield opportunities, but other opportunities. And also schemes integrated on a canal or in a water supply pipe. We will look at some of these site configurations. So as we know, runoff river schemes are when where the turbine generates electricity as and when the water is available and provided by the river. When the river dries up and the flow falls below some predetermined amount or the minimum technical flow for the turbine, generation ceases. So every turbine has a minimum requirement. For example, if you have some kind of turbines, at least there should be 10% of the flow, rated flow, or 20% of the rated flow sometimes. In some turbine types, which we will be discussing later, you need at least 30% of the rated flow to start generation. If when you don't have that flow, you have to shut down. So hydropower is like that. Hydropower, some turbines cannot work with very minimum flow. You have to have at least some guaranteed amount to begin the generation. So medium and high head schemes are schemes use weirs to divert water into the tank. It is then conveyed to the turbines via a pressure pipe or penstock. Penstocks are expensive and consequently this design is usually uneconomic. An alternative is to convey the water by a low slope canal running alongside the river to the pressure intake or forebay, and then on a short penstock to the turbine. That is the general configuration of a high head project, high head to medium head project. If the topography and the morphography of the terrain does not permit the easy layout of canal, a low pressure pipe can be economical option. You know, when you instead of a tunnel in a large hydropower project, we use a canal. We use a canal, usually a concrete canal, to bring water from the water diversion location to the forebay tank. That is the normal option. But sometimes, to bring this tunnel is very difficult. Build this tunnel is very difficult because of the terrain. Terrains are very slopy, or maybe the soil is so loose, and therefore the construction of a concrete canal is difficult. In such cases, people use low pressure pipes, which are not necessarily steel pipes. They may be FRP pipes, fiber reinforced plastic pipes, FRP pipes, right, which can be used as a instead of a canal. Sometimes they can be economical also, and they need not to carry any pressures. It is just water flow. Therefore, we can have, instead of a canal, a low pressure pipe as well. Right? So, and as usual, we release the water back to the river at the end of the power plant, or what we call the tail race. Here is a high head scheme, right? High head scheme, a schematic view. It shows the elevation and the plan. So when you have a cross sectional view, you can see small weir. We don't want to have a big pond, because when you have a pond, there will be a backwater increase and inundating other people's land boundaries. So we want to keep just enough diversion so that the water enters the canal or the channel, right? So water enters here, right, on the side of the dam, and then it is brought, right, and you can have a tunnel or a canal, right. So you can see, if you look at the plan view, is the pond, the water is diverted into the, right, so water normally flows this way in the river, and now water is diverted using the weir or the dam to a canal, and the canal runs this way, right. And in this particular project, they have opted for a tunnel when they encountered the hill, right. That is an option. But if you find tunneling is not possible, we can go around the hill. again the tunnel can be extended to go around the hill and come it, right, because the tunneling is not very technology is not very abundant in this part of the world. But if you go to country like Norway, they are experts in tunneling, right. So I have traveled up and down in many parts of Norway. So now they don't have winding roads when they are going in hilly areas, right. They don't have winding roads to go up and come down. They straight away go through the hill. So there are hundreds and hundreds of tunnels in road network of Norway and maybe in other countries also, right. I have seen whenever you travel, you go through many tunnels, because the tunneling technology is advanced. There are many subcontractors and service providers where if you ask them, they will come and have the tunnel done. And also they are these hills are very rocky, suitable for tunnel building, not like loose soil, right. So they are both advantages. So in those countries, even for mini hydro, they use this kind of a tunnel rather than using a canal, right. But in Sri Lanka, for example, if this opportunity comes, they would have opted for this, going around the hill with an extended canal, because that is cheaper and you don't have to have the tunneling technology. But in this particular project, they have opted for tunnels, right. And then you have the forebay tank, right, and penstock and the powerhouse and the tail race. Tail race is where the water is released back to the river. So this is an option, you can see when you have an opportunity, right, when you have an opportunity. And in a low head scheme, they are typically built in river valleys, right. Two technological options can be selected. Either the water is diverted to a power intake with a short penstock as in the high head scheme, or the head is created by a small dam provided with sector gates and an integrated intake powerhouse. We will see some of these things diagrammatically. Here is a low head scheme with still with the penstock, same arrangement, right, same arrangement, you can see. So here is the reservoir, and usually in any powerhouse, whether it is high head, low head or medium head, whatever, we have in addition to the desilting basin, desilting basin will take out sand and silt, right, it will take out sand and silt, but not the floating objects like leaves and logs and other things, that will not be filtered out. So you need a trash rack. Here's a trash rack, right. So trash rack is a mesh, right, mesh, and the mesh size depend upon the particular turbine. So if something is going in, it should be able to go out, right, without blocking, right. So that is the criteria. We will look at the criteria of designing this later, but anyway, it is a mesh. So things will be accumulated here. So in Europe, etc., it's expensive for them to have people here. Normally a man will stand here with a long stick or something, and he will drag them out and take out onto this and remove it. In Sri Lanka, there are many people employed this way, trash rack, at the trash rack, right, in the forebay tank, where they continuously clean, right, whatever the falling leaves and other objects. But in Europe, I have seen they use automated trash racks. So there is a machine which will come every 5 minutes or 10 minutes as programmed. So they will program it to be more frequent in the season of leaves falling and all that, and it will just come here and drag everything up and go on doing it many times, right. Automated trash racks are there, right. Okay. So anyway, then the clean water will come in here just like any other, and the penstock is here and the water flows through it, and you can see this shaft brings out, which is connected to the turbine here. Turbine is here, right, inside. So it is connected to this shaft, and shaft is connected to generator. Generator is in air, right. Turbine is there. So there is a water seal here where the axle comes out or the shaft comes out, right, and connected to the generator. And these turbines are, we are going to discuss turbines later, types of turbines. So these are called reaction type turbines, right. So, the other type of turbines are the impulse type turbines, which we are going to have a separate discussion under different topic, right. And here the issue is, the problem is not the problem, the characteristic is the head is considered as the top level water level and the downstream water level. The head will be this, right, downstream water level and upstream reservoir water level. So, that will be the H. But if you take a high head scheme where the 4 bay tank is there and you take out the pipe and the water comes and hit the turbine, then the water jet comes and hit it. So, the head will be top water level in the 4 bay tank and the jet level, water jet level, not the tail race water level, right. That is a high head project using impulse turbines, right. But here in a reaction type turbine, usually I am sure you have heard this word, Francis Kaplan machines are reaction turbines. So, they are fully immersed in water and the applicable head is lower reservoir water level and the upper reservoir water level, the difference, that will be the head. In the impulse type ones, for example, Pelton turbines or turbo turbines, it is the jet level to upstream water level, right, head. So, this is possible in existing dams, existing reservoirs, etc. And also the head will be medium or low head, right, but the Q will be large, therefore, you have a sufficient capacity. Right? Okay. Here are some other configurations, you can see the elevation here, right. There are gates, etc., right, and then the trash rack cleaner, and you need sometimes fish passes for the environmental reason, right. And then you can see here the section AA, right, here the powerhouse generation, section AA, right. Here you can see here is the powerhouse, right. This is the generator and this is a vertical axis configuration. So, in hydropower plants you will see both configurations, horizontal axis configuration as well as vertical axis configuration. Especially in large hydros, it is a vertical axis arrangement, because if you have a horizontal axis one, the weight of the generator, weight of the turbine, etc., will be too much on the shaft, because they are very heavy and shaft might deflect, right, Therefore, in large hydros, usually it is always large hydro machines vertical axis configuration, but in small hydros you can go for both. It is a design option, right. Horizontal axis is always a cheap option, right. So, but this is due to this particular arrangement, they have opted for vertical axis configuration. Generator is up here, so it is axis here, right. So, this is the axis. So, this is a Kaplan turbine. So, water comes through the trash rack, enters here in this chamber and then goes through the turbine. Turbine blades are here, right, and goes out, tail race, right. So, it is a Kaplan is one version of reaction turbines, They can be used in any configuration suitable. There are power plants which are having a penstock and then ending up into a Kaplan turbine, but the penstock will be slightly bigger, because and also it is low pressure, because the penstock they have low head mean low pressure. You do not have to have expensive steel penstocks, you can have a FRP pipe, fiber reinforced plastic pipe, right. So, they are available now commercially for hydropower development. They are fabricated in many parts of the world, especially in Europe, and they are economical compared to steel penstocks. They are much more economical. So, in Sri Lanka I have seen several power plants which use FRP pipes as penstock material, right, penstock material for low head projects under similar conditions, right. We have your head maybe 20-30 meters, right, even less. So, in that case this configuration is good, right, and also these materials. So, these are in addition to developing high head projects. That earlier we looked at high head projects where you have hilly area and then you have the contour lines to get the various heights, and then develop a project with a diversion weir canal. Canals may run into 2 kilometers. I have seen projects 1 to 2 kilometer long canals, and the penstock can run into 1 kilometer, right. So, they can be that long. As long as the economic sense is there, they will do the project, right, they will do the project. But these are very short, these are short and in a small area. You do not have kilometers long canal, maybe 20-30 meter long penstock, because head is small now. You do not need naturally long penstocks, but the diameter will be large. I will show you some when we discuss penstocks. We will see how some of these FRP pipes are used in low head schemes. I will show you some photographs. But they have their own disadvantages. You know that once we had the problem, we had I was managing a company and we had a low head power project done in Sri Lanka, and it was in operation, but we found that water was leaking. The penstock was buried. Penstock was buried, and penstock was FRP pipes, right, and buried pipes. And then we found it is leaking inside somewhere, and also that soil is coming inside, right. So, we immediately stopped and opened up the that buried areas and looked at. Then we found that pipe is damaged, and we later learned that now gradually people have used to use the area, because of this covered area, for various purposes. Among other things, heavy bus has been coming that area and has been turning at that point, because that was an open area. So, the bus have been constantly coming, stopping there and reversing and turning everything on this pipe buried area, and that pressure was too much, and that damaged the pipe. So, we had to replace that portion of the pipe. So, if it is a steel pipe, that would not have happened probably, but since it is a FRP pipe, you have to be careful when you bury it, etc., and not to have people going there and doing various activities with heavy equipment, and the pressure might damage the pipes, right, pressure might damage the pipes. So, here is a existing dam, right, how to build a small hydropower plant, that water release from existing dams and reservoirs. So, I have seen similar opportunities. In every reservoir there is a irrigation, even in powerhouse power plant system there is a irrigation outlet, because you have to release water for irrigation purposes. Even if you collect water for power generation, irrigation release is a must, right. So, they have a pipe at the bottom, right. So, water is just released. So, I have visited one of the power plants in Sri Lanka and given a proposal some time back how to insert. You can, so in the same pipe you can insert a machine. You can just cut the pipe and insert a machine in between, right, machine in between, so that the pressure, you can see there is a head here, you can see H, right, Q is here, that is what we want, right, that is what we want, right. So, you can generate electricity constantly, otherwise wasted energy, right, otherwise there are a lot of similar reservoirs in Sri Lanka. Now, in a few already there have been power plants inserted, in a few of them already power plants have been constructed, right, and more on the cards, because now the energy is expensive and high head opportunities and medium head opportunities are not there. Therefore, it is more beneficial to engage these things in existing reservoirs. Maybe in India also there may be many hundreds of opportunities. Maybe the 21,000 estimate by the Indian government, this kind of things are not included yet, right. You go for this kind of things once you are exhausted with, you have exhausted all the existing high head, medium head projects, right. First you utilize them, and because they are more economically viable, and when once you have no other opportunities, you can go for all these existing dams and other things, where you can just insert a machine in a already existing water release pipe, like irrigation releases or drinking water releases, or whatever other ways of water releases for other needs than power generation. Power generation water will be taken by another intake through a canal or a tunnel to the same system that we discussed earlier, right. This is in addition to that. This power generation is in addition to that, the regular power generation. So if you have a water canal, okay, open canal running water, right, because the water flows because of the slope, So you can insert a machine. You can see here you can see you have taken this section is developed. This is the canal, normally water is flowing, right. In a normal canal, water is flowing, water flows because of the head. We are going to use that small head. So you can, of course, you need to keep a bypass when the machines are in maintenance and other things. You will have to close this section, power plant section. Therefore, you keep a bypass to be used in maintenance times, etc. Otherwise, you put water inside and your turbines, etc. here, generator here, and then release water back to the same canal. So you can have number of them, right, number of them serially along the steep section of the canal, or these are maybe probably man-made canals in irrigation schemes, right. But you know that in the coming years, when the energy is going to be more expensive and we need to go for renewables, etc., will pressurize people to go for even 100 kilowatt, 200 kilowatt kind of applications to be developed, as that because of the high prices of energy, they become economically viable. Therefore, a company will come and say they will sign an agreement with the irrigation department. In all these canals, we will install turbines wherever the opportunities are, and they will pay a royalty to the irrigation department for utilizing their water. They will say 20% of the earnings from this scheme we will give to irrigation department, right, and the balance we use for our investment. So the irrigation departments also get an additional income, right, by leasing out their canals to be used for hydropower generation. So these are the models coming up. It is happening in already Sri Lanka. In Sri Lanka, there is a river called Mahavali River, and where very large power generation projects have been developed already. So therefore, there is a authority called Mahavali Development Authority, and so they have many irrigation schemes. Now they have allocated or leased sections of those rivers like this to mini hydropower developers who have put their money, invested their money to develop projects, and they are paying royalty to the Mahavali Development Authority, right. That is a negotiated one, but the owner has a power purchase agreement with the electricity board, and he sells energy to the electricity board, get the income. Out of that, 10% may be going to the irrigation authority or Mahavali authority or whoever the owner of the irrigation canal. So it is a successful model, right. It is a successful model. So these are opportunities other than the high head projects. We are discussing other opportunities other than the high head projects where we can develop small hydros, right. Here is a now sometimes ancient dams, etc. are not very attractive for for doing construction work, for archaeological and historical reasons. So if you propose to drill them or cut them or insert pipes inside them, archaeological departments and irrigation, whatever the other religious institutions, others will be extremely opposing doing any construction activity inside the dam, because they are 1000 years old. In Sri Lanka also there are dams which are 1000 years old, right, 1000 years old. Therefore, no one wants to touch them, right, no one wants to touch them. Therefore, what happens is we can have this siphon action. I think as we might have experimented that if you fill this pipe and let the water flow, it will continue to flow because of siphon action. So, initial water flow you have to do with some pumps, employing pumps. You have to initially fill water by keeping the end closed, right. You can keep them this side valves closed and then fill water, right, fill water, and once it is done, water started to flow, it will continue due to siphon action, and you can keep a turbine and generator here. So, you are not touching the existing dam, right, you are not touching the existing dam. So, this will be preferred in ancient reservoirs having archaeological value, where due to historical reasons no one want to dig into them to do the construction, right. So, these are also on the cards in the future when the we don't have opportunities for hydropower new projects. So, these are the final options. Okay. So, I have allocated the balance part of the today's discussion to answer any questions that you may have, right, answer any questions you may have. Also, I would like to add a few more points.
Good afternoon, sir.
Good afternoon.
It's been very informative. If at all, if we go with the calculation with respect to P, that is P is equal to efficiency into density into gravity into the length, height, sorry, then how we are going to fix that efficiency? You had shown up
Yes.
In the previous sessions that you have taken it as 0.75,
Yes.
that is 75%. Is that a constant or it depends upon any other factors?
Okay, good question. That I will go to one of the previous slides for the clarity. Here you can see, efficiency in hydropower plants has many components. So, I would say efficiency is equal to, efficiency is involved wherever energy losses are there, right. So, the first energy loss will be in the penstock because of the friction and also due to bends, and there will be any other turbulences in the valves, etc. All will introduce loss of energy. When there is a valve, it will oppose water flow and some energy will be lost due to friction. If the pipe walls are not very smooth due to say corrosion, etc., there will be more energy losses. So, there will be first term will be the efficiency of the penstock, right, energy loss, and then comes the turbine efficiency, right. Turbine efficiency, I will show you a separate diagram, I will show you. So, because when the water hits the turbine, all the energy cannot be imparted to the turbine, some part will go out, right, there will be some water going out carrying energy, right. Therefore, the efficiency of the turbine, and then when the energy transfers to the generator. Sometimes there may be a gearbox also. If the speeds do not match, in some projects you have a gearbox. If there is a gearbox also, there will be energy loss. But even if there is a direct couple, then you have the generator efficiency, right. So, the efficiency of the generator comes in, right. And then you might have a step up transformer, right, step up transformer to increase the voltage for transmission. So, you have a efficiency of the transformer, right. You may have a short transmission line or short or long transmission line from your power plant to the nearest grid point. So, there will be a efficiency of the transmission line, right. So, when I say 75% efficiency in general is the combination of these things. Sometimes you might not have a transformer, you might use the same low voltage. In that case, that term will not come, right. Typically, if you look at efficiency of the penstock will be about 95%, that is 0.95. I will skip turbines. Generator will be also, as electrical engineers we all know, generator will be about 96% efficient, present day generators. Transformers, if you see, present day transformers about 98% efficient typically, right. If you take the transmission line, again it may be 97%, maybe 3% loss if the transmission line alone, right. So these are the, so why I skip turbines is, turbine is totally different. Turbine is totally different means, now even if the generator you take, from no load to full load, there will be a slight difference in the efficiency, right. But in case of turbines, this is not the case. Turbines, full load to no load, huge difference in efficiency. So I will draw efficiency curve here with the water flow rate and the efficiency for different turbines. We will look at the same when we discuss about the turbines separately, but because of the question I will answer. So if you take a Pelton turbine, efficiency curve will be something like this, right, reaching out to almost say 93% efficiency, maximum efficiency of, right, if you take a Pelton turbine. But if you take a Francis turbine, the curve will be like this, right. So this is the 100% flow rate, this is 50% and so on, 75%, maybe 25% flow rate, rated flow rate, right. So you can see, so at part load, say 50% flow rate, efficiency of the Pelton turbine is almost 90%, but if you take the Francis turbine, it may be say 75%. Part load efficiency is very poor. If you take a Kaplan turbine, it might be in between, right. If you take some other turbines like that there are turbines called pumps used as generators, they will be very worse, right. Therefore, when you use efficiency for power calculation, as per our equation, right, turbine efficiency, you can't put a constant value. You must see what is Q and select what is the efficiency and put that value. Therefore, this curve, complete curve you have to use, right. Using curve fitting technique, you have to make a formula or something, right, and then use that efficiency using exact efficiency corresponding to the Q. We do not have to do it for transformers and generators, etc., for penstock, etc., because from no load to full load, difference may be 1%, right, 1%, not very significant. But for turbines, it is pretty significant. Therefore, we have to use the correct efficiency corresponding to the operating point. These curves you can get from the manufacturers, right. You can when you are buying equipment, you can ask him what is the efficiency curve, or there are typical efficiency curves also with the long experience. There are typical experience curves, but you can, if you search the net for turbine efficiencies, you will see set of curves like this, though that will give you the exact values, top values. Normally all types of turbines come to the maximum efficiency, about small hydros come to about 90%. Large hydros may even come to 93-94% maximum efficiency. But the part load efficiency depends upon the type of turbine. And also you can see Pelton turbines can start operations with about 5 to 10% flow rate. But if you take a Francis turbine, you must have at least about 20-25% of the rated water flow available to start operations. Otherwise, the turbines cannot operate. So, there is a minimum requirement, but in that case, the Pelton turbines are better. There is another version called turbo turbines, which you may not have very much heard. That is a recent development. Recent mean about 20-30 years back. A British company called Gilks, they developed this technology, because Pelton turbine technology is 150 years old. They are very old technology, Francis and Pelton. But turbo was developed in 1990s. Right, 1990s by this company. They had a patent for some time, but now they have many people are producing turbo turbines. So, it is something quite similar to Pelton turbines and impulse turbine. We will look at that when we discuss about types of turbines. I hope now you understand the efficiency matter.
Yeah, thank you, sir. Thank you so much.
Sir, you have shown so many different designs. So how those designs are actually affecting the power generation? Means which one is the better? And so that is the first question. And second question is, sometimes there is a load frequency control. So how these turbines and generators are playing role in that?
Okay, about different configurations, I must say it is rather location dependent, right? Location dependent. So, an hydropower expert must visit it, and with his long term experience, he must do the selection of the type. And not only that, the selection will finally depend upon the economics. Sometimes for a site, say Q is rated flow is say 5 cubic meters per second, right? H is 200 meters. Now you have the option of going for 1 turbine or 2 turbines or 3 turbines or more, right? So, that is an option, right? So, going for 1 turbine might be bad sometimes, because if you have a large machine which is operating at low loads for long time, your efficiency will be bad. Therefore, if you have two turbines, they will be operating somewhere at a higher efficiency point, right? Therefore, having 1 turbine may not be the best option, but it has the advantage, you don't have to have so many control systems. If you have multiple machines, for each machine you must have control systems, generators, synchronizing breakers and everything. Therefore, finally the final configuration we decide based on the return on investment. We do design 3 projects with 3 configurations and see which is bringing the highest return on investment, not on the economics. But other than that, there are technical issues in the construction. For example, if your location is far away from a good road, you have to build roads, and your road building is also expensive. Therefore, you don't build fully fledged roads. And if you have a very heavy component to be transported, then you will have to have very good roads, and it will be expensive. Therefore, when you don't have good access roads to your power plant, you tend to have multiple machines. Then your cost of the weight of your largest component will be less. In a hydropower scheme, heaviest component is the generator. Right? Therefore, transportation of the generator is the issue. Right? If you look at the large hydropower plants, they don't transport the generator. They manufacture generator windings, everything separately, and build the generator at site. They bring the casing, etc., because the casing is not very heavy. The heavy part is the core part, the iron core and the copper windings, etc. So, they bring copper windings, etc., part by part and assemble them at site. Turbine they bring at a 1 unit, because turbine is not the most expensive part to transport, right? So, therefore, the configuration and the final decision will be mostly based on the economics, return on investment. And your second part, you talked about some flow frequency thing. Can you again repeat that part? I couldn't get it.
Just load frequency control, sir. LFC.
Yeah, for what?
LFC issue.
For what you mean?
Load that they are coming in picture when the turbines and generators we are talking about. Also, there is something called droop characteristics. So, can you explain? Actually, I am not good in what is the droop characteristic. Now, you have shown there is a generator, this is a turbine. So, but when I see the block diagram,
Yes.
so in the block diagram, where the droop characteristics will come from these diagrams, what we have shown, sir.
Yeah, that is true. You know that in the group settings and other controls will be decided based on particular governor characteristics. But small hydropower projects, we don't normally do the the frequency control or anything. These are normally operated at unity power factor, and then connected directly to the synchronized directly to the network, and generating the maximum possible, and we don't want to be sensitive or control the frequency, because these are 1 megawatt, 2 megawatt or less than 10 megawatt kind of machines. They are just connected to the network, and the network operators are not worried about the stability issues, because these are small machines. If it's a large machine like 50 megawatt, 100 megawatt, they will want to do a separate stability study as to how the machine will behave under different conditions. But for small machines, they are not worried about these characteristics. They just permit you to connect to the network.
Okay. Thank you, sir. Thank you very much.
Okay, welcome. Yes. Any other questions?
Sir, actually, if you allow me, I have two sets of questions. First question is, sir, this type of low head scheme, can we go for the multi-generator system?
Yes. So I told you that. Yeah, I told you that I have visited. I have really seen a project in Rhine River, where they have this. It's a very wide river. So they have a dam here. Similar setup, and on one side now water level is high. If you look at the cross section, I can draw it here. I will draw it here. So water level is high on one side. Other side water level is low because of the dam. And now they put a machine here, similar arrangement like this, and they put many machines, right? And in this particular case, they had a river pass, this boat pass also. They now no boats can go up and down when you have the dam, because there is a water difference now. So they have a trap here, where the boat comes, and then you pump water to lift it up, and then pass it on to the other side, right? And the reverse, when the boat goes to the other side, you go there and get it on the other side and empty the water and bring it to the other level and release it. Because in those rivers, lot of log and other transport activities happening. So they need to have this flow. But when you have the dam, you have the water difference, height difference. The boats cannot pass. So they have to have a separate arrangement. So there's a cost also, there water pumping, etc. Right. So these things are there. Therefore, multiple turbines are possible, and that is being done. I have seen projects with such multiple turbines, series of that. And these are the these things are done in the last part of hydropower development, right? Because the head is maybe 2 meters or 1 meter, ultra low head projects. But the queue, enormous queue, right? Enormous queue coming up. Therefore, P is high. You can have sufficient P power. Q, because of the Q is high. Okay.
Sir, next question is how to select, so many turbines are there, so how to select turbine type for low head schemes? What type of which is suitable?
That we will discuss, discuss during our turbine discussion.
Okay.
So there are turbine selection charts by IEC also has given, and manufacturers also have given turbine selection charts depending upon your rated flow and the head. So sometimes you can choose multiple turbines type, then you can select it as per your option. But we will discuss about turbine selection charts at the appropriate point, right, in our discussion.
Sir, in case of small hydro projects, that is for run for river scheme, under run for river scheme, you had described that channelized water will be fed via penstock to the powerhouse to generate electricity.
Yeah.
So is there any concern taken about the pressure or flow rate of the water during summer season?
Yeah, during the summer season, water flow rate will drop. Water flow rate will drop and your generation will go down. So you have to expect it. You have to expect it. So if you take, if you expect, can see the, if you look at a typical generation of a power plant in Sri Lanka, January, February, March, it will be low generation. Then April upward, it will be high generation, right? So you have to expect this because you are fed by the monsoons, etc. So, but what you are looking at the total generation in the year, sigma, right? So that will, if that is economical, that create economic sense, that is enough. That is enough. Now in Sri Lankan context, not now, earlier, once upon a time, there was a tariff, feed-in tariff scheme where the rates were high during this period. We call it dry season tariff, and wet season tariff was a little lower. So these are devices, you know, that to keep the people encouraged, and so that you get sufficient income to run the power plant. So they gave two tariffs, dry season tariff and a wet season tariff. So these are options the governments and the electricity boards can exercise to see this seasonal effect, right? So in Sri Lanka we receive two monsoons, south, west and northeast. So different regions, different power projects get different, differently affected by the two monsoons. Some get both monsoons, some get only one. So depending upon that, you will depend, your income levels will be different during different months. But for the economic calculation, we are looking at the total energy. So we will be discussing that the energy calculation later, right, in a different discussion.
Thank you, sir.
Any other questions? Online participants also. You may even type into chat, so I can take it up maybe at some other time even. When we have a spare time, extra time, I will extend the lecture and take up some of these questions in addition to the normal lecture part.
Hello, sir.
Yes, please.
Sir, I have a doubt in while you calculated, we had an average flow rate calculation.
Yes.
But then why did we go for the average flow rate?
Yeah.
The rated flow instead of going for the...
Yes, yes. Yeah, okay, good question. You know that average, we don't build, that I agree with you, we don't build power plants for the average flow rate. It will be always little higher than the average flow we go. But this is, you know, we are doing from office an initial estimation to see whether there is a project. If with the average flow rate, if there is sufficient capacity like 500 kilowatt, 1 megawatt, then we know that there is a opportunity for a project. But you know, we never invest in a project with this average flow calculation, right? We will go for a once we are convinced there is a project, we will employ a hydrologist. We will employ a professional hydrologist to estimate daily flow rate based on 30 years backward data, right? And then ask him to project what will be the best average flow rates we can, average daily flow rate we can expect for the next 20 years. So he will give a, you know, flow prediction like this for every month, Jan, Feb up to December, and days, all the 31 days, right? He will say January 1st expected flow rate can be 1.2 cubic meters per second, and then 1.3. Likewise, he will give for the entire 365 days, right, 3.1 and so on. So we will use this for the plant sizing, calculation of rated flow, etc. But that average flow calculation was to be done from office at no cost just to see whether there is a project. But for this hydrological study and these things, we will have a separate discussion, right? How to do employ a professional hydrologist and get his report and use his data for the calculation of energy, and also a curve called flow duration curve. From this one we will have a separate discussion. That is the way that really we do it. But what I described this morning is only for initial checking of a site from office, once you have the access to contour maps and some kind of rainfall data. I hope I am clear.
Yes, sir.
Thank you very much.